Superstorm Sandy proved what can happen in terms of coastal destruction better than any PowerPoint theory book and the world watched. We all saw breached shorelines in New Jersey, houses swept away, cars floating out of tunnels, subways that resembled submarines, riveted us to television. And 2 days after Sandy hit, I was interviewed live on British morning television, the Sky News Sunrise Show, pictured here. And the anchor gave me 5 minutes and he asked me 2 questions. He said, first of all, he said, Mr. Englander, he said, your book came out 1 week before Sandy, which hit 2 days ago. And on page 121, you describe a superstorm hitting Atlantic City and explaining why that would devastate New York. How did you predict that a week before it happened? If it hadn't been 3:30 in the morning here, where I was on the internet with him, I might have had a more clever answer. But instead I told him the truth. I said it wasn't a prediction, and I was as stunned by the timing as anybody. It was just one of many scenarios I was using to illustrate how storm damage on top of sea level rise, on top of high tides at times, and when that aligns with extreme tides, lunar high tides, make things even worse. And the particular example of New York, a place that people don't think of in terms of vulnerability, was to show that on top of that there are geologic and topographic situations which make things way beyond normal. In the case of New York, it's that Long Island and New Jersey form a very broad funnel, and with a storm hitting that location, it tends to focus the intensity on New York. And worse than that, invisibly, is that there's a long, shallow, underwater coastal shelf there, and with a storm coming from the southeast, as Sandy did, water would pile up to extreme heights. With a Category 4 storm, it would have been a 30-foot wall of water. As it was a 10-foot wall of water. And his second question was, well, don't you think they should have been prepared? And I said, no. You can't prepare for a 10-foot wall of water from a storm event, which is a random chance event to some degree, in any location of any intensity, in any time period. But it gave me an opportunity in the remaining part of the 5 minutes that they gave me, which is a good chunk on morning news, to say, but what we should be preparing for is sea level rise. Because that sleeper issue, which is going to be very slow, but sure, is going to be the one that's going to catch us off guard, because it's certain. And it doesn't just affect New York, or Miami, or the Bahamas, or the Maldives. It affects every coastal city in the world, from Manila to Monaco, from Boston to Bangladesh, and cities that are coastal, not coastal, but on tidal rivers, like Washington, D.C., or Sacramento, California. Places we'd never think of. That was the point of that example. What I want to talk to you about is the particular first one of sea level rise. When we look at the coast, when we're at the beach, it's an illusion. Not that the beach is an illusion, but the illusion is that it's permanent. It's been there about 6,000 years, for as long as sea level has been at the present level. But there's an illusion of permanence. There's a second illusion, by the way, that we have maybe 5 or 10 feet of margin, but of course that is an illusion because the elevation falls off behind the beach, back down to the intercoastal and out toward the Everglades. But I want to deal with the illusion of permanence and explain to you why sea level is going to rise even if we get greenhouse gases right. And even if we do the valuable work of this adaptation plan that's being talked about today in this very important workshop. And even if we adapt, we have to understand where things are headed. If we do the right things, we'll be better prepared and we'll reduce the rate of rise. If we don't do the right things, the rate of rise will increase. We are unfortunately past the point of stopping sea level rise. And that's clear when you look at it in a geologic time frame, which is the perspective that I use in the book. I like longer time frames. They provoke clarity. Just like stock prices. If you get caught up in day trading and seeing what stocks did yesterday, you can get fooled. If you look at the longer term trends, unless you're a day trader, you tend to get a better picture. And with climate, none of us gets to be a day trader, unfortunately. This is over a century. It goes back to 1850 to 2010, so almost a century and a half. There's no doubt that sea level is rising. The line warbles. If you look carefully at the upper right, the rate of rise is accelerating. It's doubled in the last 30 years. But to really see the potential problem with sea level, we need to step back. We need to go back to the last ice age. In fact, we need to see the pattern of ice ages and realize that we haven't just accelerated climate change, we have changed the direction. And so, you may have seen the documentary series, I don't know if we call it documentary. My daughter Rachel, who's in the room here, had me watch this many times, and this was the second segment of Ice Age. This was the meltdown, the second of the 4-part series. And while a kid's movie, it's based upon some truths, which nobody disputes. And behind those mastodons, there's 2 miles of ice that covered North America and Europe. And as you melt 2 miles of ice, about 10,000 feet, and I just talk in approximate numbers. I'm not going to give you precise numbers. We look at the geologic graph from dozens of data points around the world, and we see an amazing story with 3 takeaways. One is that 20,000 years ago, in the lower left, sea level was down 390 feet below the present. 120 meters. And it didn't rise smoothly. In fact, if you look in the middle of that chart, 14,000 years ago, there's a big vertical blip, if you will, that's labeled Meltwater Pulse 1A. But what's really interesting is this all happened by nature, no impact of man. So there's a natural cycle when things can change pretty abruptly too. Sea level rose 65 feet over 4 centuries. That's 1.5 feet a decade of vertical rise, non-stop, non-return, for 40 decades. Can you imagine that? And we're warming 55 times faster now than happened at any time during the last 10 million years. To put that in visual perspective, in the book I talk about a 47-story building. I decided it's time to actually show you one. That's the Miami Tower from downtown Miami. It's the one with the colored lights, very pretty architecturally. It's 47 stories, 600 feet tall. We are, to use that as a gauge of changing sea level, we are at the line just above center, present-day sea level, about the 30th floor. That's where sea level's been for about the last 6,000 years. No wonder we think it's permanent. Our culture goes back, what, 6,000 years? That's our earliest written records, go back 6,000 or 8,000 years. Gets back to the Old Testament and other documents in Chinese and Egyptian and Turkish writings. That's how far we back we go. But then there are those fables and tales in the Bible and elsewhere about the flood and how the ocean rose. And it's interesting because it's across all cultures. And do you think maybe they were describing that Meltwater Pulse 1A? I do. When all the ice sheets melt, which somebody this morning alluded to, I can't remember, it was a great series of presentations, I think it was Jim or somebody, but maybe it was Jennifer. We will have 212 feet of sea level rise. That's not our approximate, that's the best current estimate with some pretty good satellite altimetry and understanding of the size of the ice sheets, which keeps getting better and better. But regardless, whether it's 212 feet or 192 feet, the problem's still the same. It adds another 17 stories of sea level rise. That can't happen this century. It can't happen next century. And we don't know whether it can happen in 300 years or 3,000 years. And when people say, well, how come the models don't know that? Well, models have to be validated against some kind of experimental proof. We have never, in 500 million years, warmed the planet this quickly. We're running the experiment to see how quickly you can melt the ice sheets. Our projections get better and better. I think this single graph, and I don't have very many graphs here, this isn't really a science talk. I'm going to try and give you a big picture of why what you're doing today is so important at the grassroots level. And I'm also going to leave you with, I hope, a little bit of inspiration that this isn't all doom and gloom. But this graph is three different things, color-coded. The greenhouse gas in green at the top, that's CO2. In the middle is temperature in red, logically. And at the bottom, in blue, is sea level. 420,000 years in alignment from left to right, the present day being on the right. And what you can see about the three different up and down graphs is, are they in alignment? Right? Aren't they synchronized? The peaks are pretty much on top of each other. There's no doubt that's random chance, that maybe they just happen to happen in the same 1,000 years. Why? Well, scientists need a cause and effect and a mechanism to make something a good theory. It's pretty simple. CO2 is a great greenhouse gas, as Jennifer and others talked about this morning. In fact, it wasn't proven by Al Gore, and it has nothing to do with any government agenda. It was proven by a physicist named Joseph Fourier in 1826. Fundamental physics. It has amazing heat trapping powers. If we didn't have the 1 part in 4,000 CO2 in our atmosphere, Earth would be 60 degrees colder Fahrenheit than it is today. It has amazing insulation powers. So the problem is, we've increased the concentration from 1 in 4,000, which it was for the last 10 million years, to 1 in 2,500. We've increased the rate by 40%. And as several people this morning talked about, what I'm trying to do with this book and these talks is to take really complicated science from lots of different disciplines and turn it into language that anybody can understand. And you people here have a greater than normal understanding because you're very interested in the subject. But I want to give you the tools and the language and the metaphors and the examples to go out and talk to other people. I came to the conclusion a few years ago that more information was not better in this case. Intellectually, and probably all of you in this room think, if I can just give that denier 10 more arguments, he'll get smart, or her, right? It doesn't work. You're arguing with the intellectual part of the brain, and they're deciding they don't want to listen with the reptilian part of the brain, it turns out. It's true. The amygdala, sometimes called a croc brain. And we have to get through the croc brain. We've got to teach a crocodile. And we shouldn't be talking to the environmentalists and the people concerned about this. We need to be talking to the other people. But I would also submit to you that we don't need to convince everybody. If you really get some dyed-in-the-wool denier, or somebody who is just so partisan about this that if Al Gore says it, it must not be true, or I don't want to believe it, move on, find somebody else. We don't need 100% of the people to understand the problem. Civil rights was not solved by 100% of the American people getting it. We need to swing about 10 or 15% of the people. So I hope that guides your thinking. I'm sorry, let me go back to one other point from this slide. The range of each of these things is very cyclical, and it goes with the Ice Age cycles, which is roughly a 100,000-year cycle by nature, something called the Milankovitch cycle. You don't need to remember that. But it's caused by a difference in solar radiation, the amount of heat we get from the sun. And the cycle ranges between 95 and 125,000 years. I call it a 100,000-year cycle. What I didn't know until I started writing this book and trying to explain this better, you know, when you go to teach something, you understand it better yourself. I'm sure those of you who teach realize that. That I assumed that a 100,000-year cycle was 50,000 warming and 50,000 cooling. It's not. These graphs all show it. It's a 2080 cycle, roughly. It's 20,000 years of warming, ice melting, and sea level rise. And then it's a slow, gradual decline to the next ice age of 80,000 years. Again, round figures. So here's the problem. We've just finished the 20,000-year warming cycle. We should be entering the cooling phase, headed toward the next ice age 80,000 years from now, which would be a big problem for us. But we're not going to see another ice age. We've solved that problem. And it's because in the upper right, that little green vertical tail, as you saw this morning in several of the presentations, we've taken CO2 from the normal range of 180 to 280 parts per million, and it's now at 394, I think, by last count. It just goes up 2 or 3 parts a year, and it's accelerating, and that's the problem. And I submit, my only disagreement with wonderful Jennifer's explanation is that CO2 is not an indicator of climate change, it's actually the cause. And I think, for me, people like single, simple, focused things, and CO2, of the 30 or so greenhouse gases, to simplify it, is the one that we change. We know how it correlates with energy production. It's the one we need to teach people. The public should know 394 and what it means, 394 parts per million. That's like knowing the Dow Jones of the day. It's a single indicator number. And it's not evidence of climate change. It's the cause of climate change. And it's not going to go down quickly, and we can't pretend that we're going to stop all fossil fuels today. But it's the indicator that everybody should learn to focus on. It should be on the evening news, on a banner in Wall Street, because it's the thing we changed. Because we're at 7 billion people and heading to 9 billion. And I take a very pragmatic view of it. Let's get on with it, because we can see where things are headed. Let's improve it, but let's deal with it. People always ask, how do they know CO2 percentages and temperatures thousands of years ago, before we had instruments and thermometers and stuff? Well, conveniently, nature stored a database. For about the last 15 years, geoscientists have been in Antarctica and Greenland drilling ice cores down to the bottom of the ice sheets. And snow packs into ice, goes into pressurized ice from the weight. And the air bubbles are micro air samples. And those little bright spots in this sliver of one of those ice cores has air samples. And we can get them, just like going into a tree and getting tree rings, we can get them to within 2 or 3 years of accuracy of their date. And from that we can actually see what was the carbon dioxide level and see how it varies 180 to 280 parts per million. Temperature is a little more complicated because, of course, we know the temperature of ice, but it turns out, just like radiocarbon dating, which works with isotopes of carbon, that there's 2 isotopes of oxygen, and not to make this complicated, but just to give you some validity, oxygen 16 and 18, and by looking at the ratio of them, it's a proxy for temperature. So we have a temperature record stored in those bubbles. And the fact that they're the same in Greenland and Antarctica, different sides of the planet, and that they're the same, corroborates and validates the whole system. Different teams of scientists from different countries doing different ice cores in different ends of the Earth come up with the same analysis within points of difference. I don't want to give you a science lecture today. I want to make sure that you have a couple of examples that you can use in your toolkit. And let's go back to sea level rise, because of all the things of climate change, particularly here in South Florida, it's the singular issue. And it brings it all together, because as the world's climate changes and there's snowfalls here, there's droughts there, and there's floods there, what people haven't really thought through is that the ice, the cryosphere in the scientific term, but the ice sheets and glaciers are the final or ultimate proof of long-term temperature change. Because as the ice sheets melt, the sea level rises. And we can really go and find old sea levels underwater and up on cliffs. And once we discount or back out the subsidence or uplift of the land, we can find ancient sea levels moving up and down 600 feet. So it's a really neat system because it all comes together. And it's really hard to argue. The melting Arctic, many people believe, contributes to sea level rise. Many of you probably know that it does not, because it's floating sea ice. But most of the public thinks it does. What it does do is prove warming. And it also accelerates the warming, because it's a positive feedback loop, because as you turn bright white ice into dark ocean, the planet heats up more. But I think of all the facts about the Arctic that really get me, is that it will be ice-free in September, the warmest month of the year. Sometime between now, 2030 is kind of the farthest estimate because it keeps getting faster and faster. And 2016 is the latest estimate. 3 years from now. The fact that the Arctic will be ice-free and it has been frozen for 3 million years should give us pause. Just a nice visual to lighten that is, this is the North Pole, this is the Russian submarine and some of the local inhabitants, just to give you a visual confirmation that this is not ice on land, which means that it's not, just like ice cubes in a glass, it will not raise the level of the ocean. We have to look at the big ice sheets and glaciers, and these two Google Earth images prove irrefutably where the ice is, Greenland and Antarctica, 99% of the ice in the world. And as that ice and the little bit of glaciers melts and works its way to the ocean rises. There's also something called thermal expansion. As the ocean warms, about half of the 8-inch rise in the last century has come from the actual warming of the ocean. The ocean is an average of 2 miles deep, and as most things warm, there's a microscopic increase in their size, and that's happened to the ocean. But that issue is going to pale in comparison to melting the ice sheets. Strangely, melting the glaciers is not big stuff. If you melt all the glaciers in the world, you get about 2 feet of sea level rise. So again, that may be a little disconcerting to think about, because maybe you thought it was the Arctic ice cap or glaciers. I just want to give you enough facts and keep them simple and visual so that you're comfortable with the facts, and when you look at this or explain it, it makes sense. In Greenland, you've probably seen photos like this. I was there in 2007, and there were about 100 of these moulins, these vertical chimneys, which have carved their way as the ice melts, and the sheen of meltwater coalesces into streams and finds cracks and carves out vertical chimneys, moulins. There were about 100 in 2007. And as that water gets down beneath the glaciers which normally grind away very slowly on bedrock and boulders and gravel, they're lubricated. Now it's on a sheet of water, as that illustration shows. And colleagues who were there last summer, 2012, say there's now about 1,000 moulins carrying the meltwater down to the base of the glaciers. And the glaciers that they measure have doubled or tripled in speed of carrying ice and therefore water to the ocean, which will raise sea level. But we're still talking millimeters a year. But just like interest rates or anything else that keeps compounding, therein lies the problem. It happens each year, and if it keeps happening a little bit more, it's a problem. And to give you a sense of scale, of the 100 glaciers that take the horizontal ice sheet in Greenland, and just terminology, there's 2 ice sheets in the world, big ones, Greenland and Antarctica. Okay? Glaciers are the rivers of ice, which in many places take the ice sheets and bring it to the ocean slowly. Okay? So just a terminology issue. 2 mega ice sheets, and there's over 100,000 glaciers that are monitored in the world. But there's about 100 in Greenland, and one of them, some of you have been to it, the Jakobshavn Glacier, or Ilulissat Glacier, puts enough fresh water in the ocean every year to take care of the entire water needs of the United States. They're huge.
It's in a day.
In a day.
Not a year.
Thank you, John. I need to speed up. We have to get back to the next part of the program. Antarctica is a different problem. Antarctica, parts of it are growing, but parts of it are getting warmer, and it potentially has the capacity to really accelerate sea level rise. Antarctica is not in the projections. The scientific projections that you read, including the 4-county report based upon the Army Corps of Engineers study, is all based upon minimum projections. They're actually optimistic. Some people think they're worst case, they're not. They don't account for dynamic ice sheet changes in Antarctic, and even in Greenland, they're only up to a limited amount of melt rate increase. The sea level itself is rising faster than the projections. This is the bottom line. If you look at the top red line, that's the trend line smoothing out the gold line, which is sea level, since 1990. The projections are all shown in blue and green, below the red line, within 20 years we shouldn't be exceeding or at the top boundary of the projection range. That's simple proof that the projections are conservative. We don't quite understand why things are melting this quick, so the models don't quite reflect it. I can see despair on some of your faces. This is a troubling subject, and I say in the book it's a little bit like finding out you had a terminal disease or something like that, or a serious disease. We have to deal with it, and I think we're really surprisingly adaptive, and I think therein lies another good metaphor, which I want to conclude with. But just to give you the big picture for a second, if you look at sea level rise over the long-term history of the Earth, on the left, back in the days of the dinosaurs when there was no ice on Earth, when Alaska was as warm as Florida, sea level was hundreds of feet higher. For the last 10 million years, and specifically the last 3 or 4 million years, we've had these cyclical ice ages, as I already showed you. It goes up and down 300 or 400 feet. The last time it was high was 120,000 years ago at the last peak, and actually then it reached about 25 feet higher than today. We're going to blow way past that. We, as the graph kind of shows in a dotted line, we don't know exactly because we don't know how much carbon we're going to put in the atmosphere over the next century. So that's why projections can't be exact. When people say, well, they didn't even know how much it's going to rise, it's going to rise 2 feet or 4 feet or 3 feet or 6 feet, tell me how many people, tell me how much coal, how much nuclear, how much solar we're going to be using by the end of the century, and I bet the models can get a lot more accurate. So what's the story of the century? The story of the century that the TV news forecasts or broadcasts with their sound bites miss is this. And I missed it until the book was done. I would have titled it differently. It's not about sea level rise. Sea level rise and the shoreline are flip sides of the same coin. But the shoreline moves at least on an average of 300 times to 1 for each foot of sea level rise. Here in Florida, it's far more than that because it's so low. So, this is the story. After 6,000 years of stability, the shoreline is starting to move inland. And it's going to move inland for centuries, and it has before. We've just changed the direction because we should be actually seeing a receding shoreline. It's not. We can change the speed now. We can't change the reality. And of course, we're a coastal society. Any place in the world, this happens to be New Zealand, there's huge developments on the coast. I could pick any place in the world. And we've all seen, or many of you have seen the illustrations from Miami, or Hollywood to Miami, what happens with 1 meter, 3 feet of sea level rise, which we will probably have this century. A lot of land goes underwater. So I come to a simple conclusion. There's 2 things we need to do. We need to adapt to a slowly changing shoreline. And I don't necessarily think that's the worst thing in the world. It's just very disruptive. But it doesn't matter whether I like it or not. It doesn't matter whether I want it to happen or not. And it doesn't matter whether you want to find out, well, what could we have done to stop it? I submit to you that here we are on March 2nd, 2013. We really need to focus on the future, as you are here and as the RCAP is doing. And we need to come together to look at how to adapt and how to slow it. Because that's just reality. It's going to take new engineering solutions, new architecture, new social issues. 100 years from now, Florida may not have the population it has today. We may go up and we may come down as sea level intrudes on the water table. We've never understood that before. And then, of course, we should try and slow the rise, the greenhouse gas reduction, energy efficiency, and all the things, transportation change, all the things that are built into that RCAP. Absolutely. I talk about 5 points of intelligent adaptation in the book, and because I'm running over and it's 1:30, I'll kind of skip through that. But we need to look at a long-term perspective. We need to recognize that the projections always have ranges. We need to recognize that certain areas are going to have unusual vulnerability and surprising places, that government bailouts are probably limited because the government can go in and fix storm surge. When sea level rises and doesn't go down for over 1,000 years, it's a different problem. And it's universal. It hits every place equally. And at some point, coastal properties will be adjusted, but they're not going to be catastrophic, is the good news. I thought they would be. I don't think they will be. I think they're going to go down very slowly. as people realize that they have a limited life. In business, you can look at asset protection or risk avoidance. You can also look for new opportunities once you see a new reality on the horizon. And there will be places to make money. There will be winners and losers, just like in any big change. And the sooner we see what's on the horizon, some people liken it to a tsunami, the more we'll seize opportunities. And then there's opportunities to communicate. What we're doing here, my book, other things. A lot of you are involved in that. And if I can facilitate that, I will, but you'll find better ways to do it. Often the polar bear is used as a symbol and the reason we should care. I've had a personal experience with polar bear that if I had more time I'd tell you about. I survived it, but it doesn't matter. And while I really like polar bears, it'd be nice if they stayed around. Species come and species go. I'm far more concerned about our species. And that's not to be callous. I've been to the Arctic many times. It's really an important and dramatic place. But the polar bear is the least of our problems. It really comes down to the question of our legacy. This problem is going to go on for centuries. And what we do today, now that we have the knowledge, is the issue. And future generations, kids and grandkids, will look back and say, what were they doing? It's a question many of you asked. Gore and others have asked it. It's an obvious question. But it's also a reason not to give up hope. Because change is going to happen, folks. And we have to find a way practically to deal with it. And having worked on this for 5 years and this message, both the research and then writing the book and all the things that went with it, I struggled with how can I not leave people depressed? No, what is the positive image or message? And I came out with 3 silver linings to the very dark cloud. One is most crises that we have to deal with give us no warning. Tornadoes, tsunamis, earthquakes, even big hurricanes give us a couple of days. We can't change our society with that. This is a bigger problem, but we have years and decades to adapt. That's a blessing. We can figure this one out to the degree that you can deal with a problem. But the second is that humans are amazingly ingenious when we focus on a problem. We're adaptable. You know, we think we couldn't survive if we were an amputee or if we had cancer or chemo and all those things. And we all know we survived that. We're amazing. And we'll come up with new technologies, whether it be battling AIDS or battling cancer or putting man on the moon or you know, new ideas on terrorism. We're going to do great stuff. But the first step in doing great stuff is to focus on the problem and not delay and deny. Which brings me to the third thing, that I truly believe that while things will get worse in the decades ahead, we will do some incredible stuff when we're gone, in generations to come. But I think even in our lifetimes, we could be challenged by sea level rise, or I'll say shoreline moving inland for the first time in 6,000 years. And maybe actually figure out some better ways to govern ourselves. Because this is one problem that you can't ignore. It's the first major change in our livable area in human history. It's a little hard to say it doesn't matter, or this will go away, or this is a construct of Congress, or one party versus another. So in those 3 points, I hope you share with me the opportunity, like finding out from your doctor that you've got a problem. We may go home and cry and drink and sleep for 3 days. Then you go back and say, okay, what do we do about it? And today most of us survive medical problems because we got great technology. It's not a matter of what I want, it's a matter of what I see that is. Whoops, sorry here. Wrong direction. So my last slide, I'm way over time. What can you do? You can do what you're doing today. You can find ways locally to support really good plans that have been put together. Whoops. Really good plans. It's only water. A little sea level rising. You can do what you're doing today to work together across sectors, from government to environmental groups to faith-based groups to community action groups to citizens, and say, how can we work together to adapt in this place which is particularly vulnerable? You can also spread the word. You can protect your assets. Now, sea level rise, the other good thing is, it's not going to change tomorrow. I mean, let's be real about it, okay? We really, if you say, well, now that I understand, I'd like to maybe sell out that one piece of property I got in the keys, fine. Say, over the next 10 years, you're going to do that. Somebody else will come along and buy it because they want to be there. That's okay. That's the marketplace. That's not the end of the world. You can adjust your assets, your companies, and your communities to recognize the long-term change. But you can also help get the word out. This is transformative, revolutionary information. I can see by the faces here that I've changed your perception of it today. It's a different perspective than we look at 10 or 20 years out. And by that revelation, our attitudes change. This is way beyond me. I've just put together an interesting case that connects the dots for people and puts it in a long-term picture. I can't do this alone. People like you need to carry the message. Whether you buy my book, it's $19, $20. It's an ebooks for $9. But take it, learn from it, give your own talks. This is going to take a lot of people. But I do believe that we can deal with it once we confront it and understand it for what it is. So thank you for helping me spread the word. I appreciate it.